Welcome to this session on the discussion of the so-called quantum phase estimation algorithm. Now, the quantum phase estimation algorithm is a special case of an application of the Fourier transforms which we have discussed earlier, and it is a key to a general procedure which allows us to actually extract the eigenvalues of a given operator. So suppose now that you have a unitary operator, and this unitary operator has a set of eigenvectors and eigenvalues. So assume now that you have this operator and that acts on an eigenvalue. And since this is a unitary operator, it has an eigenvalue, which we write like a lambda times this vector u. And this lambda is now given by e of 2 pi of I times phi. And phi is this unknown phase, which we are going to estimate using this phase estimation algorithm, or the quantum phase estimation algorithm, just shortened to the QPE algorithm. So this quantity phi, the basic recipe here, is a two-step recipe. So we're going to encode an unknown phase with a circuit that produces, as a result, something which can then be identified through the quantum Fourier transform. And then when we have applied this transformation of the state u, then we're going to, at the end, to apply a joint of the quantum Fourier transform in order to find the phase phi. So this quantity phi is the unknown one. And if we now look at the standard eigenvalue problem, if we have an operator A acting on U, we know that this is given by the standard characteristic polynomial, which is the result of us calculating the determinant of A minus lambda times the identity matrix, and this is set to 0. So the quantum phase algorithm is the one we are going to discuss a little bit more in detail now. So the basic procedure of the quantum phase estimation algorithm is, one, to encode an unknown phase, encode the unknown phase phi, with a circuit. And this circuit is a circuit which is going to produce a result which is identical to the result of a quantum Fourier transform, which we have discussed earlier. And we are going to interpret the resulting qubits as parts of a binary fraction. So let's repeat quickly here. Encode the unknown phi with a circuit which then produces a result which is identical to the result of us applying a quantum Fourier transform. Produces a result identical to a quantum Fourier transform, to a QFT, which we discussed the earlier weeks. Now, the next step is to apply the adjoint of this operation in order to find the phase phi, to find phi. And this is essentially the basic steps. So to detail step one, what we are going to do then is to define a register which has t qubits. So we would define, this is normally called a register with t qubits, so it's a given number of qubits. And if you remember back to what we discussed in terms of the definition of the quantum Fourier transform, we encoded a state given by J0, J1, so these are the different bits which defines a specific state, up to Jn minus 1. This is something which we would encode in terms of a floating binary representation, which means that we would have, and then depending on which one we define as the leading qubit, and we would have Jn minus 1, Jn minus 2, up down to J0. And this, as we remember, is given by 1 divided by 2 times Jn minus 1. And then we have 1 divided by 2 to the power of 2 of Jn minus 2, etc., down to the last qubit. Now, this means that if we have t qubits in this specific case, so in our case, n, which we have set up here, is going to be equal to t. We know that we cannot represent in a classical computer all possible floating point numbers. So with a given number of bits, t in our case, we can represent a given number to a certain precision, because this is represented when we transform a decimal number in decimal representation to the binary representation. We cannot always map the numbers exactly to a binary representation. Just to give you an example, if you take 1 divided by 10, 0.1, that cannot be represented exactly in the computer in terms of binary numbers, this equation which you see here, with a given fixed number of qubits. And since we always have to deal with a fixed number of qubits, it means that there is an approximation error here. So when we use the quantum phase estimation algorithm, one of the bottlenecks or one of the drawbacks is the fact that we are going to use a certain number of qubits to represent the quantum Fourier transform. So just keep this in mind, because that's going to be one of the approximation errors which come into play. Now then, when we have set up these qubits, we are going to perform a Hadamard transformation on each qubit so that we get a superposition of qubits 0 and 1. And then we add to this a second register, which represents this eigenvector u. And then we connect this register to a sequence of these t qubits. So we make a t instances of this unitary gate u. And each one takes us to increasing powers of 2 as we move on, up to 2 to the t minus 1. And that's similar to the QFT. We connect these register qubits as controlling gates to the unitary gates. And to achieve the powers of 2, we multiply this u, this operator, which is acting on the state, with itself and accumulate the results. And the whole procedure is something which we're going to set up a little bit later here. When we have performed these Fourier transformations, at the end, we are then going to perform the adjunct operation and recover the phase phi, the unknown quantity. So the first thing which we're going now to do is to define this register of t qubits, which means that we are going to perform a transform on these. So to set up this in a schematic way, you could now think of having a set of t qubits, which is the first register, and these qubits are prepared in the state 0. So we go down here to t qubits. So we have t in total. And then on each of these, we perform a Hadamard transformation so that we get a linear superposition of qubit 0 and qubit 1 when we perform the Hadamard. And then we can just continue this all the way through here. And then we have the second register, which then represents the states whose eigenvalue we want to define or we want to extract. And this is also represented by a set of qubits. And then in each stage here, we're going to perform a unitary transformation. And in this particular case, we are going to perform a unitary transformation on the first qubit. And we're going to have a 2 to the power of 0 here. We are going to have the next one. So we have a u of 2, 1, etc., all the way till we have interacted with the last qubit. So this is a operation which now acts on 1 qubit at a time. So we would have a next qubit in here, and that gets transformed, etc., till we have the last qubit which is acted upon by this unitary transformation of t minus 1. And then we just mark this by this controlled operation. And at the end, we end up with a given modified single qubit states, which we then use to recover the relevant information. So when we look at the representation of these qubits, so this phi is now going to be represented by the phases which we will have for each one of these, or the qubits which we have. So this will be phi 0. If we choose this ordering, phi 1 and phi 2 up to phi of t minus 1. And that means that what we have now is phi 0 multiplied with 1 over 2 to the power of 1 plus phi 1 divided by 1 over 2 to the power of 2. So now we are choosing the opposite labeling, which compared to what we put up previously. And then we have a phi of t minus 1 or 1 divided by 2 to the power of t. So this is the basic algorithm. And with these kind of preliminaries, we actually now able to see what is going to happen here. So you can think of a given state, if you have just one qubit in the register with t qubits, or you can just think of looking at one of these qubits. So what we have then is a state which we are preparing here. And we perform first a Hadamard transformation on this specific qubit. And that produces a new state, which we can call psi of 1. And then we perform this unitary transformation. And we mark that one with a u, 2 to the power of 0, just to indicate that this is the first phi 0 point. And then we have the controlled operation. And then we continue with the Hadamard gate here. And then we end up with a final state psi of 3. And then we have a final state psi of 2 in here. And these are the typically the kind of basic operations which we end up doing. Now, to get some kind of feeling of this, let's start with you having a very simple eigenvalue. So that means that we have an eigenvalue which is now defined by just one qubit. So we have an e of 2 pi of I, and then we have 0 times phi of 0. So this means that in our specific case, we can represent a number depending on the value of phi 0. So if phi 0 is 1, we can represent 0.5. And if phi 0 is 0, we have 0. So with just one qubit, the precision of the phase which we can estimate just gives us two possibilities, 0 or 0.5. So if we keep adding qubits, we are obviously going to get more and more and a better precision for the final result, phi. So what this means is that when we now perform the operations for this state phi psi 1, which we had in the previous graph, that is going to be given by the tensor product of the Hadamard transformed state 0 and tensor product with the state psi, which is the one whose phase we want to extract. And that means that what we end up with then is 1 over square root of 2, which comes from the Hadamard gate. And then we have 0 tensor product with psi plus 1 tensor product with psi. And when we now put this in, or plug in the results from the operations with the exponentials, we end up with psi, and we are writing this in a more sloppy notation, plus e of 2 pi of I, 0, and phi 0, multiplied with 1 and psi. Now, what we see now is that the phase factor, the way it works in this kind of quantum Fourier transforms, it's actually irrelevant whether we look at this qubit 0 or 1, which we have, and the state psi. So we can also rewrite this as 1 over square root of 2. So this would be the same as us having performed the Hadamard transformation plus an operation with a rotation gate on the second qubit, on the qubit state 1. and multiplied with the state psi. So this is what we normally call the result of a control U operation. So if we go back to the graph here, when we look at this graph, this state psi is now, after we perform the Hadamard operation on the state with qubit 0, we get a superposition of qubit 0 and qubit 1, and then we perform the U operation on that gate. That's a control U gate. So after the control U gate, we have this state psi2, and this state psi2, so the first state is this psi1, and psi2, where should I put up that one? This is a state which we get after we have performed the control U gate from the previous graph. So that's the control U gate. And then afterwards, we can perform a new Hadamard transformation. But if we look at this state psi2, we observe now that what we see is this psi2 is that the state psi remains unmodified, as it should, since it's just an eigenstate of U. And that means that we can apply this U as often as we want. And psi, the state whose eigenvalue we want to extract, remains unmodified. However, the eigenvalue has turned into a phase of qubit 1, and this part of the first qubit is then modified. And last week, or the week before, we actually discussed, we call this the kicked phase to qubit 0, which was something we introduced when we discussed this type of transformations, the quantum Fourier transformations on a given qubit. So there's still a problem here, is that on measuring the first qubit, the state might still collapse to either 0 or 1. And that has equal probability of 1/2, independently of whether the phase value is 0 or 0.5. So kicking the phase up does not change the probabilities. And to resolve that, if we go back to the circuit which you see here, we apply another Hadamard gate to the top qubit, and then we obtain this state psi3 here, which looks like as follows. So psi3, after we have now performed the Hadamard transformation on this qubit, transforms into 1/2, and then we have, so the 1/2 is just a 1 over square root of 2 times the previous 1 over square root of 2, and then we have 1 plus e of 2 pi of I 0 of phi 0, and this is multiplied with qubit 0, plus a similar factor of 1/2 of 1 minus e of 2 pi I of 0 of phi 0, and multiplied with 1 here. So when we look at this one, we see that the term phi 0 is a binary, since term phi 0 is a binary digit, it can only take value 0, 1. So if that one is 0, what it means then is that the factor, the exponential which we have, becomes equal to 1. So if phi 0 is equal to 0, remember now that we have only two possibilities, since these are binary values, so either 0 and 1, which also means that the phase we want, this phase can take values as 0 or 0.5, since we're just using one qubit now. So if that is the case, you see quickly now that the second term, which we have here, that becomes equal to 0, and it's only this first term. So we have 1 plus 1 divided by 2, and that means that what we end up with then is that psi3 collapses to psi 0. On the other hand, if phi 0 is equal to 1, the other possibility, then what happens, and we see that quickly, is psi3 collapses to qubit 1. So that means that we will now measure either 0 or 1 with a given certainty. And depending on whether the phi, the phase which we're looking at, the unknown parameters, was 0 or 0.5. So if we now move on and consider two fractional binary parts of the phase, we can now increase the precision So that means that now we would actually have to have 2 qubits in the register. So we would have a qubit 1 and a qubit 2. And in that case, we can now have values which go from 0 through 0.25, 1 divided by 4, 0.5, or 0.75. And that means that we would get a new circuit, which would look like as follows. So we would have a qubit here, which we prepare in state 0. We perform a Hadamard transformation as we did in the previous case. And we have the new qubit here. So we have t equal to 2. Now we have 2 qubits. And then we have the state whose eigenvalue we want, or eigenphase which we want to find, is psi, which is left unchanged when we performed all these unitary transformations. So the first one here is a u2 to the power of 0, and that acts on the second qubit. So it's a controlled U gate. No, sorry, it can act on the first qubit or the second qubit, but let's have it acting on the first qubit here. So this can act on this one. And we get then a new state, which we can call for psi1. So that's the total system here. Remember that the state psi is unchanged. And then we have a new operation on the second qubit, u21. So this is a new control U gate. And then we have a new state psi of 2 here. And when we perform these operations, what we will see then is the following. So if you look at this state psi1, this is going to be equal to 1 over 2 to the power of 3. And then we have for the first qubit, we will have a 0 plus an e of 2 pi I. And then now we have 0. But now we are going to have 2 qubits, which means that we have 4 possibilities for the value of the phase phi. And this is now again multiplied with 1. And then we have a tensor product with the Hadamard transformed second qubit. Remember now that the factor of 1 over square root of 2 is contained in this factor here. And finally, we have a tensor product with the state psi. So the first one which you see here is the first qubit. So we should actually have, there's a small typo here. So we have a phi1 here. This is multiplied with 1. And then we have a tensor product with the second qubit. So what you see here is the first qubit. And we have performed this controlled U gate. This is our second qubit. And then we have the final state, which is the one whose eigenphase we want to find. Now, what we know then is that when we perform a new such operation, so if we now act on the final qubit, what we call the second qubit, we would then have an operation of the type. So we are going to perform this twice now. So we have a U2 acting on psi here. And this is going to be given by an E of 2 pi of I times 2 of phi here, and multiplied with the state psi. And when we look at these fractional representations and the effects of the U squared, or U times U, what we see then is that the binary point shifts by 1 digit. So what we have is that we have 2 phi is now given by 2 times 0, phi 0, and phi 1. And this is the same as 2 of phi 0 of 2 to the power of minus 1 plus phi 1 of 2 to the power of minus 2. And that's the same as phi 0 plus phi 1 of 2 to the power of minus 1, which we will typically then rewrite in this binary notation as phi 0 dot phi 1. And then we can split the fractions at the decimal points. So if we do that, so we split fractions at decimal point. At the decimal point. And if we do that, you see that we can rewrite 2 pi of I of 2 phi, which then becomes equal to E of 2 pi of I, and then I have my phi 0 plus 0 of phi 1, which is again equal to E of 2 pi of I multiplied with phi 0, and then E of 2 pi of I of 0 of phi 1. This term phi 0 corresponds again to a binary representation. So these guys here, phi 0 and phi 1, they can take values of 0 and 1 only. And that means that the first factor corresponds to a rotation by 0 or 2 pi, which essentially has no effect. So if you look at the first one here, if we have 0 or 1 here, we get either a phase factor, which corresponds to a rotation of 0 or 2 pi, which means that this quantity here is basically equal to 1. So what we're left with then is E 2 of I, 2 pi of I, multiplied with a binary representation here of phi 1. And this can then be generalized. So if we do this many times, so we can generalize this. We generalize this to E of 2 pi of I. And then we would have 2 to the power of k of phi, which simply becomes equal to E exponential of 2 pi I. And then we would have 0 phi of k. So that gives us a very compact notation. And for our system with the 2 qubits plus the state phi 0, psi, sorry. So for this system, where we have 2 qubits in the as in the register T, so T is equal to 2 in this specific case. For this case, with T equal to 2 and the state psi, which is the one whose eigenphase we want to extract, what we end up with when we have performed these operations is that the state psi of 2 here, which is the outcome of this circuit, which you see here, this one. So we perform first the Hadamard transformations on each single qubit in this register. And then what we have is a unitary transformation on the first qubits, a controlled U. We have a controlled U on the second qubit. And then we get a final state psi 2, which is the one we later want to use to extract the final value for phi. So what we end up with then is 1 over 2 to the power of 3. And then we have 0 plus E of 2 pi of I and 0. And then we have phi 0 and phi 1 multiplied with qubit 1 state. And this has a tensor product with 0 plus E of 2 pi of I, 0, phi of I, phi of 1, sorry, multiplied with 1. And then this is, we take a tensor product with the final state whose eigenphase we want to find out. So this is the form that results from applying the QFT operator to 2 qubits. So this is a QFT operation, quantum Fourier transform on 2 qubits. In what we call the register T. And in our case, T is equal to 2 in that specific case. Now, this means what we can do now is to apply a 2-qubit adjoint quantum Fourier operator to retrieve the binary fractions of phi, and the binary fractions are given by these numbers which you see here. So with that, this is the final form, we can apply, and this gives you basically the algorithm for the phase estimation algorithm. So this means that we can apply the 2-qubit And then we have the 2-qubit adjoint Fourier transformation. The 2-qubit UFT, this is marked with the adjoint here, operator to retrieve the binary fraction of phi, which is equal to 0. And then we have phi 0 and phi 1. And this is essentially the basic operation, which now when we perform the adjoint operation, the QFT, on this specific state, psi 2, which we found, then this is going to give us back phi 1 tensor product with phi 0 and tensor product with psi here. And so to summarize, we connected the 0th power of 2 to the last qubit in this register T, and then the T minus 1 powers of 2 to the first qubits, or the other way around, depending on how we want to interpret the binary fractions. So the final state then, when we now want to generalize this, so suppose now that we express this phi in terms of T qubits, or T bits in our case, we could then have the following representation: phi 0, phi 1, phi 2, and all the way down to T minus 1. Alternatively, we can interchange depending on how we want to organize these qubits. And that means that what we would get then is a final state which runs like 1 over 2 to the power of T half. And then we would have 0 plus e of I of 2 pi to 2 to the power of 0, and multiplied with phi of 1. And then we have the next one is a tensor product of a chain of these, and we end up with the final ones plus e of I of pi. And then I have 2 to the power of t minus 2 of phi times 1. And then we would have the final one here, which is 0 plus e of I of 2 pi. No, not 2 pi, sorry. I'm so used to write 2 pi here. Phi of 2 to the power of t minus 1 times phi of 1. And that is the final state. And then we would perform a inverse Fourier transformation. Remember now that the quantum Fourier transformations are given by unitary transformations. So when we then get this phi in this number of bits by multiplying the angle with the powers of 2, as we show above, or what we are doing then is actually to shift the digits of the binary representation to the left. And we will then get a transformed state. And this is essentially the basic algorithm by which we can extract the value for this unknown phase phi. So if we now take and multiply the angle which we have with powers of 2, as we did in the 2-qubit case in the register, then we are left with the following representation, which actually looks like what we would get if we were to perform a quantum Fourier transform. So we would get something which then at the end looks like 2 to the power of t half. And then we have a 0 plus e of I of 2 pi. And then we have 0. And depending on how we organize the states, so let me just bring that one at the bottom here. So let us just quickly just rewrite it. So we have t minus 1, and this is given by qubit with the state 1, and tensor product with 0 plus e of 2 pi. And then we have multiplied with phi of t minus 1 and phi t minus 2. And then this is multiplied with state 1. And this goes all the way down to the final one, where we now have the tensor product with 0 plus e of I of 2 pi of 0. And then we have the whole chain of qubits, t1 minus 1, t minus 2, and all the way down to phi 1 and phi 0. And this is multiplied with the state 1. And in this particular case, what we have is a representation of phi, which is now given as a phi of t minus 1, phi of t minus 2. And remember now that each of these phi values can take values of 0 or 1 only. And finally down to phi 0. And we're just writing this in terms of a general phi of I, which takes values 0 and 1 only. Now, this form, which you see here, is actually similar to what we have for a quantum Fourier transform, where the rotations come out according to how the input qubits were initialized in a binary representation. So in our case, we initialized these qubits in the register T to be in the state 0 only. And then the bit indices are reversed from what we usually have seen, but you can always interchange this, the ordering here. So this is very much up to you, just to, as long as you are consistent with the way you order the bits. And the reverse from what we saw previously, but this is just a renaming or ordering issue. And the final step of this phase estimation reverses the quantum Fourier transform, so it applies a inverse quantum Fourier transform to allow reconstruction of the input, which in our case was a representation of this number phi in a binary fractions. And the complete circuit then, if we now want to set up the basic elements which would enter us writing an algorithm for a quantum phase estimation implementation, we would then have, again, this register with t qubits, which we would typically prepare in state 0. Then each one of these, to each one, we apply a Hadamard transformation. And in addition, what we have is a new register, which then contains the state whose eigenvalue or eigenphase we want to find. And this is a state which we label as a psi here. And here we could have a given number of qubits, which is used to represent it. We perform different types of controlled U operations. So we would have a U of 2 to the power of 0. And we can apply this either to the first qubit, or we can apply it to the last one. So this depends on the ordering which we have chosen. So this is just an issue of ordering. There's nothing deeper than that. Then we have a nu of U of 2 to the power of 1, which then would act on, so let's just give in a line in here. So we have a new one here. And these proceed so that we do these operations for all the qubits which we have. And you see now also why this type of algorithm is really an algorithm which requires very long circuits. And this is one of the reasons why we use the VQE at the end, because this is going to give us pretty long circuits. And most likely the states which we're going to prepare may not be in those states which we would like them to have after all these computations. So we end up with a final control U gate here. And then what we do then at the end is to apply a inverse quantum Fourier transform on these qubits in the register T. And we mark this one with a inverse quantum Fourier transform, which was not clear enough on the drawing here. So we should write it like this, QFT inverse. So this is a unitary operation. And then from that one, we can extract the faces. And we can reconstruct the faces. And this is essentially the algorithm which we are going to implement in project number 2, for those of you who would like to do that. The algorithm then, if we want to spell it out in words, let's try to do that. For the QPE. So the first set is actually to define a box of operations which perform a controlled U operation for a given number of integers. And then we have an eigenstate of this operator U, which then has a specific eigenvalues. So the inputs here is a given number of qubits for the register T, or T register. And these are those which we want to apply a controlled U operation on. So we need to specify that. We need to have this state which we want to operate on. So we have this operation U, which needs to be defined. And then we have an eigenstate, which we don't know actually, but we know that these eigenstates are given by e to the power of 2 pi I multiplied with a phase phi, since we are applying a unitary transformation. And then when we have these inputs, what we need to set up then as outputs here, that is an n or a t qubit representation of the final phase. So it's a t qubit approximation to the phase phi. So remember now again that if we have 2 qubits, we can represent four numbers in a binary representation. And these t qubits, they take value 0, 1. And if I have 2 qubits, then I can represent a phase by the number 0, 1 divided by 4, 1/2, and 3 divided by 4. So the runtime here is normally something which goes like runtime is proportional to t² operations. So compared to the operational quantum eigensolver, which we discussed in connection with project number 1, this is an algorithm which becomes much more lengthy when it comes to the number of operations which have to be performed. And we would then have one call, so all t operations, t² operations, and we would have one call to a control U gate for each of these qubits. And this, at the end, we have to perform an inverse quantum Fourier transformation. So if we're setting up the steps, then we would get a procedure which looks like as follows. So we would then have the initial state, 1. So we have the initial state, and now we are marking the initial state with just 0, even though this one looks like a 1 qubit state, but it's actually 0 for the t qubit states. And this is given by 0 with the state psi here. That's our initial state. Then we perform these superpositions. So we create superpositions. And the first thing which we do now is to perform the Hadamard gates. So we do a Hadamard on all t qubits. And we can write that in a more compact way as 1 over square root of 2 to the power of t. And then we have a j from 0 to t, 2 to the power of t minus 1. And then we write this as a j here, so this can be either 0 and 1. And then this is tensor product with the state psi. So J here is now a collection of all these T qubits. So it's a more compact notation. So if I had 2 qubits, I would write this as 0, 0 or 0, 1, 1, 0, 1, 1. But now I'm just giving that one specific label, and that represents this state here. If I have T qubits, that is given by J0, J1, J2, up to J minus 1. But we are just labeling this in a more compact notation here. Just remember the notations which we used when we introduced the quantum Fourier transforms. Then we are going to perform a operation. So the next step, we have a control U on all the qubits. So it's a control U on all qubits, T qubits. And we would mark this schematically as 1. So we get a new state here. We have 1 over 2 to the power of T. And then we have a sum from J equals 0 to 2 to the power of T minus 1. So remember now that this sum J does not run, just to remind you of the kind of notation we introduced when we wrote the Fourier transform, the quantum Fourier transform, is that this J now is now given in terms of a number, which is decoded from the binary integer representation of all these qubits. So if you have 10 qubits, you can make 2 to the power of 10 possible configurations. So this 2 to the T minus 1, which you see here, represents all the ways we can organize these 10 qubits, all the possible states. Remember that if we had 2 qubits, we got 4 possible 2-qubit states, 0, 0, 0, 1, 1, 0, and 1, 1. If we have 3 qubits, we get 8 possible states. So this is just a compact labeling of the different qubit states. Then that means that we can rewrite this one when we now perform the control U operations as a 2 pi of I. And then we have this compact notation here where I'm just going to write this as phi. And this is the angle phi which we want to extract here. So let me we had another notation here. So 2 of phi, which we then rewrote in a more compact way. And this has a J and tensor product with the state psi. Then the next step is to perform an inverse Fourier transform. So apply inverse QFT. And finally then, we measure the first register. The final step is then to measure the first register and extract what we will call a phi tilde, which is an approximation to the true phi. Because remember now that we've been using a given number of qubits to represent the exact value of phi. So with that, we have essentially the basic steps in an algorithm which we are going to construct in project number 2. And for the programming details, we would recommend taking a look at Robert Hunt's text. And this is in particular in section 6.4. And you can access this one for free if you log in with an university IP number. And that contains a description on how you would implement these different steps. Feel free to be inspired by that. And you should also in the project here try to compare that with what Qiskit produces for you so that you can see that your code is actually giving the same result as Qiskit is doing. So this is a very, compared to the VQE algorithm, this is not a very, floating point efficient algorithm as we did when we implemented the VQE. And you will see that the bigger the better the approximation we want to have, the more qubits we need. And that means, again, that we need many more floating point operations. And if we implement this on a real quantum computer, we are going to need circuits which are very, very long. And compared to the VQE, this is clearly not very beneficial for running on the type of quantum computers which we have right now. So this concludes the discussions of the phase estimation algorithm. This algorithm is an important building stone in many other algorithms. And one of the algorithms which we will discuss in the forthcoming weeks is Shor's algorithm and the ordering algorithm, where we actually use a quantum Fourier transform as a basis. Another algorithm, which is pretty well known in the community, is Simon's algorithm. So quantum Fourier transforms play a very important role. And for the quantum phase estimation algorithm, this was seen as one of the first attempts at extracting eigenvalues of the Hamiltonian systems before the VQE algorithm came on the market.